Hello guys, welcome back. Um, Today we are going to talk about Michelson Interferometer. By the way, these are my lockdown looks because there is no access to saloon or barber. So you know who did that. Okay, so we are going to talk about Michelson Interferometer and Michelson was a US scientist, physicist, and he, along with his colleague Morley, they conducted an experiment which changed the course of human science and the way we understand this universe. And the instrument that they used to perform that experiment was Michelson interferometer. So, this instrument has a great history, I would say, and I would encourage you to go to Google and find out about the experiment that they performed and the conditions why they performed that experiment. Okay, so you would know how science progress. Okay, and their experiment eventually led to um, uh, further experiments and opened up opened up the whole uh, relativistic and quantum field for the human beings. So their experiment was uh, such a big defining moment in human, um, I would say, progress. Okay. Anyways, so the point is the interferometer that they used was was a very sophisticated instrument and interferometer because it is working with the wavelength of light, which is a very small quantity. It has a very small magnitude, the wavelength so of light. So the instrument was bound to be very sophisticated and very sensitive. So because it is very sensitive instrument, the setup requires a lot of things. Okay, but we are not going to go into that, and we will look at the basic minimum that the setup would require. So it has to have a light source. It would split the light source into two parts. Okay, so this M naught is going to be a partially silvered mirror, which would send 50% light to the straight path, transmits 50% amplitude of light, and would reflect 50% of light. Okay, so this is the basic setup. The light would reflect back from the 100% reflecting mirror M2 and 100% reflecting mirror M1 and will eventually interfere at the partially silvered mirror itself, M0, and then I would be looking at it from a telescope. Okay, I will come back to this diagram again. So basically what it is doing is the setup is splitting a light beam into two parts and then it forms an interference pattern by superposing them at M0. Okay, what do we get from it? So we can measure wavelength of the light very accurately with the help of Michelson interferometer, and we can measure the length also. Okay, and but what Michelson and Morley did with this instrument was something else. Okay, so go and read about it and you would be amazed how intelligent they were. What were they trying to do? Okay, okay, so how this basic setup works. So we are going to displace this mirror one. Okay, and we are going to displace it and record the displacement, and from that we will be finding out the wavelength of the light used. Okay, so we can do this with the help of this. arrangement or this Michelson interferometer. Okay, so let's see. Uh, so what we are saying is this is a monochromatic source of light. A light beam is sent from here, and 50% of it gets reflected to the upside. Okay, and 50% of it is going straight, which is transmitted. Okay, the mirror is placed at 45-degree angle, as you can see this M0 mirror. Okay, and it is transmitting 50% light and reflecting 50% light because it is partially silvered. It means 50% of it has the you can say the finger pattern or whatever pattern, such that 50% of its surface was silvered. Okay, so 50% light would pass through the glass interface and 50% would get reflected back where it meets the silver on the back side of the glass. So this is how you make the mirrors. Okay, and these mirrors, they have 100% silver backside, so these are 100% reflecting mirrors. Which one? M2 and M1. Okay, so the light, 50% light has gone to M2 and gets reflected back, and 50% of light has gone up, reflected back from M1, and they would come back and make a dark spot here. Okay, why a dark spot? I will come to that, and actually it would make a pattern like Newton's ring, and I would be looking at this pattern from this telescope. Okay, so this is the thing that is written here, and okay, let's check out next slide. What it is saying is, if M1 and M2 are at 90 degree, right? I am talking about this. So it is saying that if this axis and this axis are at 90 degree, you would find a perfect dark spot here, then bright, then dark, then bright, then dark, and from this telescope I would be looking at this pattern. Why this pattern is being made there? Let's check that out. Okay, so I'll be rubbing this off and let's talk about it. Okay, so we will apply whatever we know about the light interaction with matter in this. Okay, so let's look at the light which is going to upside. Okay, so this light got reflected from this glass. Okay, so when it gets reflected back, I would count it as it has got a phase difference of pi or a path difference of lambda by 2, because it got reflected from a denser medium. Okay, now this light moves a distance of L1 up to here, right? And then it reflected back again from this denser medium, so it gets a path difference of lambda by 2 or a phase difference of pi again. Okay, and then it comes back to this M0 covering a path difference of L1. So twice it has covered this distance going up and coming down, and then it has a path difference of lambda by 2 because of reflecting from this denser medium, and because it was reflected from here also, it has a path difference of lambda by 2 here. So let's check out how much distance the light has covered in the up direction. So distance in up direction would be L1 plus L1 going up and coming down, right, plus lambda by 2 path difference due to reflection from M0. So lambda by 2 plus reflection from M1, lambda by 2. So it would be twice of L1 plus twice of lambda by 2. So it would be twice of L1 plus lambda. So this is the distance on the upside. Let's check out what is happening to the light which is going transmitting from M0 and going like this. Okay, and let's say that we have taken L1 is equals to L2. Both these mirrors are at same distance from M0. So this is my initial condition. Okay, let's check out the path that this uh, ray which is going in the straight direction. Okay, distance traveled in the straight direction would be L2, because the light would go from here to here and then it would come back. So L2 plus L2 plus it would be reflected back from this denser medium. So there would be a path difference of lambda by 2 because of this reflection from denser medium. And because it is not reflected from M0, it won't be having that extra lambda by 2. Okay, so D straight would be L2 plus L2 plus just 1 lambda by 2. So it would be twice of L2 plus lambda by 2. Now if I am asked to calculate the path difference here, that is delta x, net path difference between D up and D straight, so I would subtract them. So it would come out to be 2L1 plus lambda plus, no, not plus, minus, actually twice of L2 plus lambda by 2. So because L1 and L2 are same, so they would cut off and I would get lambda minus lambda by 2. So the net path difference would be lambda by 2. And we know that if two rays arrive at a point with a path difference of lambda by 2, what would be the what kind of superposition they would be doing? They would be doing the destructive interference. So this spot would appear dark, and then on some distance away from the center it would be bright and then again dark and then bright and then again dark. So a Newton's ring pattern would be formed here. Okay, so this is the basic premise, that if L1 and L2 are same distance, there would be a center dark spot here. Okay, so now I'm going to clean it off. Okay, let it come. Okay, so I have cleaned it now. The conclusion is, as I have taken L1 equals to L2, right? So my delta x is coming out to be lambda by 2, where delta x is distance covered by ray in the up direction minus distance covered by ray in the straight direction. Okay, so I would be getting a dark spot here because the net path difference is of lambda by 2, and path difference of lambda by 2, delta x of lambda by 2 means a delta phi of phi. Okay, so it would be destructive interference, a dark spot in the center of the Newton ring forming here. Okay, suppose if I move this M1 by a distance of lambda by 4, what would happen? Okay, so I would just clear some of the space here. Okay, so now in the initial condition, when L1 was L2, I found out that my delta x, the path difference is exactly lambda by 2. Now suppose I have moved this mirror 1 by a distance of lambda by 4. Okay, so let's check out what is the difference in path and what would be the net path difference. So distance of the wave going upside would be now, see, L1 plus L1, it is still there, so twice L1 is still there, plus this reflection would give a path difference of lambda by 2, and because this ray is going up to here and then coming back, right, so these two distances has to be added. So lambda by 4 going up plus lambda by 4 coming down, plus it still has to be reflected from this M1, right? So lambda by 2 from there. So d up net now will be 2L1 plus lambda by 2 plus lambda by 2. So it would be 1 lambda, 2L1 plus 1 lambda plus lambda by 4 plus lambda by 4. So it would be lambda by 2. Okay, so d up is this much now. Once I have moved this mirror by a distance of lambda by 4. So I have moved by lambda by 4 and I am getting distance on the upside like this. What about the distance in the straight direction? It is still twice of L2, right, plus lambda by 2 due to reflection from the denser medium, that is mirror 2. So it is lambda by 2. So now let's find out what is the delta x. So delta x would be d up minus d straight. So it would be twice of L1 plus lambda. So I would be cutting from here itself, or okay, I will write it 2L1 plus lambda by 2, and here it is 2L2 minus 2L2 plus lambda by 2. So because L1 and L2 are still same, right, I had taken the extra path as extra distance. I have kept L1 and L2 same. And this lambda by 2 would be cut from this lambda by 2. Okay, so this lambda by 2 goes away and this lambda by 2 goes away. I am left with a path difference of lambda. So delta x is equals to lambda when I have shifted the mirror M1 by a distance of lambda by 4. Okay, so path difference of lambda would give you constructive interference. That means this black spot would now become a bright spot at the center. So effectively what happened here is, as I moved this mirror M1 by a distance of lambda by 4, I found that the dark spot at the center has now become bright. Suppose I move it further by lambda by 4, what would happen? So I have taken this M1 here now. So total M1 has gone up by lambda by 2, because lambda by 4 and lambda by 4 would make lambda by 2, right? So the total distance, I have moved M1 by lambda by 2, and moving mirror 1 by a distance of lambda by 2 would give me delta x when I have moved mirror 1 by lambda by 2 distance. I would again get the net distance is a multiple of lambda by 2. And if path difference is again a multiple of lambda by 2, odd multiple of lambda by 2, I would find destructive interference. So this spot would, earlier it was dark, when I changed, when I moved mirror 1 by lambda by 4 distance, it became bright, right? And when I moved it again by further lambda by 4 distance, it became dark again. It means if I move mirror 1 by a distance of lambda by 2, my center spot, this spot which was earlier dark, it would become bright and then it will come back to the dark again. So it means it has made one round. What I mean by made one round is, It was dark, it became bright, and then it came back to become dark again. So if I can count the number of times it has become dark to bright to dark, and then from dark to bright to dark, what actually I am counting? I am actually counting how many distances of lambda by 2 I am shifting it. Which one? Mirror M1. I am repeating it again. If I moved mirror M1 by a distance of lambda by 2, this dark spot would become bright and dark again. If I move it by twice of lambda by 2, it will make that change twice. Which one? This center spot. If I move it by lambda by 2 and then lambda by 2, which means I have moved it mirror 1 by lambda distance, how many times this dark spot become bright and dark again? Twice. Why? Because one complete change from dark to bright to dark means is equivalent to what? M1 is moved by a distance of lambda by 2. So this is the Michelson interferometer working. What I am saying is that I would be shifting mirror M1, okay, I would be shifting mirror M1 by some distance, and I would be counting how many times this dark spot is becoming bright and dark again. Suppose I move this M1 by a distance of 5 micrometer. How do I know I have moved it by 5 micrometer? Because there is a scale fixed with this mirror M1 and this M2 too, but I won't go into that. I am not moving M2, and let's just say that I have a scale here in micrometer units, and I moved this M1 by say 5 micrometer. Okay, and during this movement of M1, I noticed that this dark spot became bright and dark again, bright and dark again, bright and dark again 20 times. Okay, so this dark spot made complete transformations from dark to bright and then back again to dark 20 times. So it has changed say 20 times. Okay, now because I know that this dark spot has to change once from dark to bright to dark, right? If it changes by one cycle of dark spot is equivalent to how much shift of M1? Lambda by 2. This is what I had written in the back slide. Okay, one complete change from dark to bright to dark is equivalent to M1 moved by a distance of lambda by 2. I just explained it here. You can revise it and look how I justified that thing. But here, if I have noticed that this dark spot has become bright and dark again 20 times, and during that I have moved it by 5 micrometer, this M1, what it is telling me? It is simply telling me that because one displacement of lambda by 2 in M1 would give me one cycle of dark to bright to dark. Okay, so if this displacement is 5 micrometer, okay, I don't know lambda here, but I do know that how much I have displaced M1. So this scale has told me that I have moved by 5 micrometer. Okay, and I have noticed 20 cycles. of dark to bright to dark. Okay, so let's rephrase it in mathematical form. So what I am saying is 5 into 10 to power minus 6 meters should be equals to 20 into one cycle of dark to bright to dark is what? It is equal to displacement of lambda by 2 in M1. So it means if I am comparing displacement with displacement, this equation should hold. Why? Because one movement of lambda by 2 would give some displacement. Okay, say this displacement. Another displacement of lambda by 2 would be equal to this displacement, and it has happened 20 times. So 20 times lambda by 2 displacement has been made in the M1 mirror. Okay, and my scale is telling me that it is equivalent to 5 micrometers. So I have to equate these two things, and now when I equate it, I am saying that 20 into lambda by 2 should be equals to 5 micrometer. So you can cut this 20 by 2 and it becomes 10 lambda equals to 5 into 10 to power minus 6 meter. It means lambda will be equals to 5 into 10 raised to power minus 7 meters. Why? Because this 10 would go in the denominator. So this is what I have found here, and this is the way Michelson interferometer counts the lambda or measures the lambda by indirectly measuring the displacement of the mirror. Okay, so it is a very clever trick, and the setup would be something like there would be a knob and you would be turning this knob. Okay, and suppose by one turn of knob this scale moved by 1 micrometer. Okay, so this is the arrangement, and if I can make such kind of arrangement, what I am doing is I am actually making a movement or giving an input by my hands or my fingers, which moves in the range of say millimeters, right? You cannot work in micrometer with your fingers. You can make a change equivalent to like millimeter or something. But what is happening is, by making a change in millimeter with my fingers in real world, I am measuring something in the accuracy or precision of nanometers, or at least in fraction of micrometers. Okay, so this is the strength and beauty of Michelson interferometer. I would advise you to go through this video at least twice to understand what I am saying, and please make sure that you go to Google and search for the famous Michelson-Morley experiment on ether. Okay, they were searching for this medium, and why they were searching for this medium? Because they wanted to find out if light actually is able to travel in vacuum, or there is some ether medium in the space also. Because till then there was an opinion that any wave which is moving, or if there is a wave, there has to be a medium. Okay, because they had seen the example of water waves, and they had seen the example of string waves, or they had seen the example of sound waves. All these waves need a medium to travel. So when Maxwell gave his laws on electromagnetics, he said that light is an electromagnetic wave. So the question was what is the medium in which light travels? So initially they thought that there is a medium, and they named it ether, and they wanted to find it out whether ether exists or not. And this is the setup that Michelson-Morley devised to find the answer for that. And what they found is there is nothing like ether. Okay, so till now, this is the beliefs that we hold. Uh, I can't say about the future, but you are welcome to pursue it further, and you would get a Nobel, because Michelson eventually got a Nobel for finding out that ether don't exist. And if you could find out that it do exist, which is not impossible, we have to keep our minds open. So you are welcome to pursue it. Thank you. I will see you in next lecture.